I'm setting up the big 63-column breadboard to move everything over from the smaller one. First thing, I grab the Raspberry Pi GPIO expansion and seat it so the odd pins 1, 3, 5, and so on line up along column D 1 through 20. The even pins sit opposite on column H 1 through 20. I press it down gently so the header's snug, but not bending the board. You can see how it eats up the middle section, leaving just a couple of free columns, A and J, for connections. I check that the rails still line up left to right, because that'll matter when I bring power in. The goal here is to anchor the Pi interface cleanly before I start migrating any of the other parts. I start with power. The 5-volt supply from the WAGO goes straight into the left red rail at row 1. Solid red jumper, neat and short. Then the ground from the WAGO drops into the left blue rail at row 1, using a black lead. These two rails will carry the LED strip's main power. Next, I seat the big 4700 microfarad capacitor to buffer those current spikes. Long leg to the left red rail at row 3, short leg to the left blue rail right beside it. That's my energy reservoir, ready to smooth out the voltage when the LEDs pulse. Now I connect the ground bridge. A black jumper runs from the left blue rail across the center gap to the right blue rail, both at row 10. I chose row 10 because it's a nice neutral zone, not too close to the GPIO header at the top or the chips further down, and the jumper lies flat and clean without crossing any wires. I'm starting with the Raspberry Pi expansion plugged into the breadboard, pins 1 to 40 sitting neatly across D and H columns. Now I'm taking the white jumper from pin 1, that's the Pi's 3.3 volt supply, and sliding it straight sideways into the right red rail at row 4. The wire sits almost flat. No tension, no bend. Then I grab a black jumper from pin 6, ground, and plug it right into the right blue rail at the same row 4. That way. My power and ground lines are short, direct, and tidy. The top 3 rows stay open for the bulk capacitor and the WAGO pigtails on the left side, so nothing feels crowded. The Pi GPIO expander is already plugged in. Its pins stretch from D1 to H20, with a little overhang at 23. I'm leaving rows 21 through 27 open as a breathing space, a clean corridor for signal wires. Now, I pick up the SN74HCT125N level shifter and drop it across the center gap, starting at row 28, with its little notch facing toward 21. That placement keeps the chip body clear of the Pi header and gives me room to route jumpers neatly underneath. I double-check alignment. Rows 28 to 34 look good, and press it down gently until it's snug. This open zone will make future wiring easier. Short, tidy runs from the Pi pins and no crowding against the expander. I'm wiring the SN74AHCT125 level shifter for the LED data line. First, I give it power. I take a red jumper from pin F28 on the chip and land it on the left red rail. That's my 5-volt line. This is what lets the chip output a solid 5-volt logic high for the LEDs. Next, I ground it. I run a black wire from pin E34 to the left blue rail. That gives the chip its ground reference. It's 0 volts, the baseline every signal depends on. Now I enable the first gate. Pin E28 is the 1 OE bar, which means it turns on when it's pulled low. I connect E28 to that same blue ground rail. By doing that, I'm telling the chip, stay active, always pass the data through. If this pin were left floating, the gate could chatter or drift off because of noise. If it were tied high, the output would shut off entirely. First, I'd find the Pi's Mosey pin, that's GPIO 10, on physical pin 19 of the expansion header. I've got a green jumper plugged into D10 on the breadboard for that. The other end of this wire goes to E29, which is pin 1A on the SN74A HCT125N. That's the chip's input side for the first buffer gate, the one that handles the LED data channel. Next, I'm adding a small resistor in line between the buffer's output and the LED strip. It's a 330 ohm resistor. Nothing fancy, just a way to tame the high-speed edges so they don't cause ringing or flicker down the line. I slide one leg of the resistor into C30. That connects it directly to pin 1Y, which is the output of the first gate on the level shifter. Then I drop the other leg several columns away, over in A36. That spacing gives it a little mechanical breathing room, makes it easier to plug in, and keeps the leads from bumping into the chip body. From A36, I run another green jumper wire off the edge of the board to the data in lead of the SK6812 strip. That completes the signal chain: Pi, level shifter input, resistor, LED strip. That's it for the data path. It's a short run, tidy and electrically clean, ready to light up the strip with solid, glitch-free data when we power on. Starting with gate 2, the second output enable pin, that's 20E, sitting at E31. I grab a short red jumper and hook it straight to the left red rail, which is my +5V. That keeps the gate disabled at a solid high level. Right next to it is 2A at E32. This one should be grounded, so I take a short black wire from E32 over to the left blue rail. That's ground. Nice and tight, minimal slack. Now moving to the right side of the chip for gate 3. 30E is at F32. Since the right rail carries 3.3 volts from the Pi, I'll use that for the logic high. White jumper from F32 to right red. Quick tug, solid. Then 3A, one step down at F33, goes to ground. Another short black jumper from F33 to right blue. Next up, gate 4. Starting with 4OE, that's F29. Again, this one should be high, so white wire from F29 to the right red rail, keeping the run as short as possible. Finally, 4A at F30 needs to be low, so I pop in a black jumper from F30 to right blue, nice and parallel with the others. I'm parking the unused gates on the level shifter so they don't float. The goal here is just to tie each one to a safe logic level, keeping the wiring short and clean. I'm shifting the amp to rows 44 through 50 on the new breadboard, giving it breathing room from the level shifter up front. That gap keeps digital noise off the audio line and lets me run a clean, short 5-volt and ground pair straight from the power rail. It also leaves space for the speaker wires so they don't crowd the GPIO header, and gives me room later to drop in another small sensor without touching the core wiring. Starting with LRC on A44, that's the left-right clock. I'm running a yellow jumper from here over to D18, which is Raspberry Pi pin 35, GPIO 19. Next, for BCLK, the bit clock, I'm taking a blue wire from A45 to H6. That's pin 12 on the Pi, GPIO 18. Now for the data line, DIN. I'm connecting a green wire from A46 to H20. That's pin 40, GPIO 21. The PCM data out from the Pi to the amp. The gain pin at A47 stays floating for now. I'm leaving that one open. The SD pin on A48, that's the shutdown control. I'm tying high with a white wire to the right red rail so the amp stays powered on. Then GND at A49 gets a black wire straight to the left blue ground rail. Finally, VIN at A50 connects with a red wire to the left red rail. That's our 5-volt supply. This is how I'm wiring the Max 98357 AI squared amplifier onto the breadboard now. I've got the 7-pin header sitting across rows 44 to 50. I'm setting the TSL 2591 light sensor onto the breadboard now. Its pins go left to right. I'm dropping the header into column A, rows 56 through 61, so it hugs the edge and leaves the center gap clear for other parts. Now I'm wiring power. VN at A56 goes to the right red rail on the same row. That's my 3.3 volt line, using a short white jumper so it stays neat and easy to trace. The next pin, 3VO, I'm leaving open. That's just the onboard regulator output, and I don't need it. For ground, A58 connects straight across to the right blue rail, row 56, with a short black jumper. That gives the sensor a clean common ground with the Pi. Then I bring in the data lines. SCL at A59 goes up to pin 5 on the Pi header. That's GPIO3, the I2C clock line, and I'm using yellow to stay consistent with my clock signal color. Right next to it, A60 SDA runs to pin 3 on the Pi, which is the data line in blue. The final pin, INT, I'm leaving disconnected for now. It's the sensor's interrupt output, and I can hook it up later if I want the light sensor to alert the Pi directly. I'm adding the push-button header now. I take the small 1x4 strip I soldered earlier, it's my little blade connector, and seat it neatly along the right edge of the breadboard so it doesn't crowd the GPIO expander. The pins go into column J, rows 24 through 27. I orient it so pin 1 is at J24. That's my signal pin. I mark it with a tiny dot to keep things straight. Pins 2 and 3 stay unused for now. Then I grab a short green jumper and run it from J24 over to D6, which is GPIO 17 on the Pi. That's the button's signal line. After that, I finish the ground return, a black jumper from J27 to the right blue rail at row 27. Clean, tight connections, nothing crossing awkwardly. This way, the button wiring stays compact and easy to see when I power things up. I've got the LED strip power leads here, and I'm wiring them into the WAGO blocks. The idea is simple. Give the strip the cleanest possible path to power, so every LED gets the same bright, stable voltage. First, I take both of the red wires from the strip, one from the female connector, one from the voltage adding lead, and plug them together into the same plus 5 volt WAGO. This block is already tied to the power brick's plus 5 V line, so now all three are sitting in one shared connection. You want the metal inside the WAGO to really bite down on the copper, so push the wires in firmly until you feel that click. Then I move over to ground. I take the 2 white wires from the strip, the return lines, and seat them into the GND WAGO. That block's tied directly back to the power supply ground. It might not look like much, but this parallel connection actually lowers resistance at the head of the strip. It's like giving current a wider highway, which helps prevent voltage drop when all the LEDs light up at once. Before I move on, I give each WAGO a gentle tug test. Nothing should slide out. Then I follow the pigtails from those same blocks. One red jumper running out to the left power rail, one black to the ground rail. Now I am connecting Raspberry Pi GPIO expansion. Orientation matters a lot. Upside down will swap odd even rows and can put 5V where ground should be. Bad day. The Pi PCB usually marks pin 1 with a tiny square pad on the underside and often a small silkscreen 1 triangle near the header on top. If there's a groove, convex groove, keyed shape on one long edge and a smooth edge on the other. Manufacturers often put the odd row on the keyed side here. A few millimeters of exposed gold pin is fine, as long as the contacts are fully engaged. You should feel a solid seat. Typical 2.54 millimeter headers make reliable contact with 1.5 to 2.0 millimeter insertion. I've got the multimeter out, black probe plugged into E34, red probe into F28. The display settles at about 4.5 volts. That means my supposed 5-volt rail is sagging a bit by the time it reaches the level shifter chip. So I start thinking through the usual suspects. Maybe the ZK4KX is sitting in current limit mode. Then I move the red probe over to E28, leave the black in the left blue rail, ground, and check again. 0 volts flat. That tells me the one output enable pin is pulled low properly. The buffer's active and not floating. I've got my multimeter set to continuity mode. One probe on D10, the other on E29. It reads about 0.17 ohms. That's basically a dead short. Exactly what we want. The tiny resistance you see is just the meter leads and contact points doing their thing. Now I'll move the red probe over to A36, where the resistor steps from the shifter's output. The display settles at 329.5 ohms. Perfect. That's our series resistor, right in spec at about 330. It means the data line's protected and ready to drive the LED strip without ringing or overshoot. Type sudo I2C detect Y, and wait a second. There it is. Address 0x29 shows up on the grid. That means the sensor's alive, powered, and talking over I². Now I'm testing the audio path through the Max 98357A amp. I open a terminal and run speaker test with no options, which by default plays infinite pink noise on a single mono channel. The console starts spitting out timing lines. 48 kHz sampling, one channel, pink noise. Then you can hear that familiar hiss in the background. The numbers scroll. Front left, time per period equals about 2.73 seconds. That tells me ALSA is streaming correctly. After a few moments, I stop the test, Control+C, and it throws the usual interrupted system call message. Totally normal. It just means I ended playback manually. Next, I run a more formal check. That switches the test tone to stereo wave playback. One loop only. The output confirms 2 channels, 48 kHz, 16-bit little endian. Buffer size set, period size set. Then I hear it. Front left, front right. That's the amp feeding both sides of the Dayton speaker exactly as expected. I'm running the LED test script now. The power supply reads 5 volts at about 0.16 amps, so everything's stable. Then I watch the strip. The very first pixel lights up pure white, bright and clean. A moment later, pixels 1 through 3 come alive. First red, then green, then blue. Each color holding for about a second before switching. The whole cycle takes around 3 seconds. It's a simple sequence, but it proves the chain is solid. The SPI line on GPIO 10 is talking through the level shifter, and the data's reaching the SK6812 just fine. Seeing that quick pulse of white, followed by the red-green-blue sweep, is the confirmation I wanted. SPI to AHCT 125 to the strip, all working exactly as designed.